If you like this video, make sure to subscribe to our channel and hit the notification bell icon to get the latest updates.
Okay, guys, so we'll start. I think most of you have joined. So what we are going to look at today is, so till now, what we have been doing, let this open Spider. So till now, what we have been doing is just trying to, do some querying, basic querying in Python. We have learned to some extent. But before going into any of the statistical models, it's important that we get some basic understanding of statistics, which will be required in our, model building classes, which is the core of analytics or core of machine learning, right? So for that, we need to have some basic statistical knowledge. And the way we are going to do it is, so you remember, right, that we had done something like all these functions we had seen, skewness, kurtosis, standard deviation, covariance, correlation, and like this, many other things we had done, and few more stuffs we are going to look at, which is much more relevant in terms of machine learning models. So we'll just see now that right now we just try to figure out the functions, how it works, and everything. But now we'll do some more analysis and understand a lot of other concepts in statistics. So that which will help us, coupled with our Python knowledge, how to build or how to write functions, how to use functions, how to use libraries and stuff. When we couple both of things, coupling both of things will get on to the understanding of machine learning techniques and machine learning algorithms. So I'll start with some of the basic things. One thing is so we'll keep a few things very simple. On that, we are trying to learn about variables. So variables could be of two types. As far as our machine learning is concerned, one thing is simple continuous variables, and another is, you remember from that a categorical variable. We had discussed few things about this. So continuous variables are any numeric kind of numbers which can take any numbers, right? So like, let's say that for an example, height, weight, or for an example, income or price of some cars, right? So these things can take any numbers. It can be of any kind. It can take any numbers. But for an example, let's say we talk about categorical variables, which can be like let's say something around gender, or maybe months in a year, right? Or maybe weeks in a day, something. So which takes only few values. If it is taking only few values, then we can say that, okay, this is a categorical variable. Like months can take only 12 values, weeks can take only 7 values, gender would mostly be only 2 values, right? So if it is like that, then we say that this is a categorical variable which will only take few values. Now let's imagine from the point of view of age, right? So what do you think age should be? Continuous variable could be like income, maybe whatever, weight, price. So these things will come as part of our continuous variable, which can take any numeric number, right? So age, what do you think age should be? Or maybe for example, let's say number of credit cards so a person is holding, number of credit cards with a person. What do you think these kind of parameters should be, in your opinion? Anyone would want to give some opinion on this, like age or credit cards, number of credit cards?
Should be continuous.
Okay.
Yeah, it should
And
be
how about
It should be continuous.
How about credit cards? Number of credit cards?
So continuous.
Continuous.
Okay. Okay, so see, theoretically speaking, yes, that age can start from anything, 0, or maybe you can also put something like 0.6 or 0.5 years, like half year age, 1 year age, whatever. Any number it can take, right? Similarly, number of credit card will not be decimals, but it can be like 1 or 0, right? 0 credit cards, 1 credit card, 2 credit cards, 3 credit card, anything. So it can also theoretically take any, like 150 credit cards, whatever number it can take. But now you understand it from one more context. It's not just about the numbers, right? The thing is, practically speaking, I mean, how many credit cards are you holding? Some of you might be having 1 credit card or 2 credit card, or maybe 3, 4 credit card at the max, right? Generally, we don't find people with 10 credit card or more than 20 credit card, right? Generally, it's something in the range of 0 to 5 credit cards, isn't it? Hello?
Yeah, that's true.
Yeah.
Listening.
So we just don't have to look it from the perspective of, whether it is numeric or not. We also have to see the context in which it is numeric. Like income can be any number. That's fine enough. Like someone can have $60,000 income, someone can have $6,000 income. That's fine. But then number of credit card usually numeric. It's numeric, but then still we can have, like, let's say that. So when we are doing it for the model, because everything that we are understanding is from the purpose of building models. So now in this case, how I would define the number of credit cards, like number of credit card if I'm putting, then it can be like a person has no credit card. He can have 1 or 2 or maybe 3, or let's say that after that I can simply put 4 plus. Makes sense? Because most of the things will be contained in these things, right? Almost 80 to 90% people will have between 0 to 3 cards. This is what is expected from the practical lines, right? All of you agree with this?
Yeah.
Okay. So based on this will also act as a categorical variable. You're getting my point. Though it is numeric, it can take theoretically any number. But from the practical perspectives, it can take only few values. It cannot take a lot of values. Getting it? So always what we want to do is, because we want to understand it more from the practical significance, more from the solving a problem significance. So we don't want to make it too complicated. So just to give you a gist that, like, we have to, like, these kind of things are there. We have to make certain, numeric variables into categorical variables depending upon the context. Similarly, age theoretically could be anything, but it doesn't matter if someone is, 1 year of age or 1.2 years of age or 1.5 years of age. Practically, he'll go to a pediatrician only, right? If he is to go for a doctor, based on between 0 to 6 years of age, 1 to 6 years of age, he is going to go to a pediatrics only. So from that context, we can let's say that if we defined age till from 1 to 120, we can sort of segregate it based on our context in which we are talking about. Maybe let's say that a person is in the kids category or very small age group, then he could be in the age group of 0 to 6 years. From 6 to 12 years, you can put. Then the person can get into the age of teenage, right? Then the person could go into the age of teenage. So it could be in the range of 12 to 18. So what I'm trying to say is, then person, once he goes out of, maybe he's in college and pursuing studies, so it could be like 18 to 25. And like that, the age group can go up, right? 25 to 30 you can put when he has just got the job, in the context of building the models in the or in the practical context. Let's say 25 to 30. Then you can have something in the range like 30 to 40. So based upon what we are trying to do, accordingly, we can just basically segregate all these age groups. And above 60, we can just have one. 40 to 60 or 45 to 60, we can have one kind of bracket, which can be thought to be as some kind of middle age group, right? And then you can have simply 60 plus, which can be thought to be as old age group, right? So theoretically, yes, it can take any number, but from practical perspective, it can only take few values. So we'll, based upon the situation, we can segregate and make these continuous variables into categorical variables depending upon the context. So that is something very important that we need to understand, because this is a important thing going forward. So that's why I just wanted to give you a hint of all the variables, that how it works out. I hope I'm clear till then, right? Okay. So now think of a few things. now when I'm talking about categorical variables, right? Let's say that if we talk about cars, so cars, the car companies can be counted on fingers. There are not many car companies in the world, right? You can have BMW, Tesla, whatever, few Mercedes, Benz, whatever. So if you list all of them, it will be just few numbers. It's not going to be a lot of big numbers, right? So whenever we are talking of, and similarly, if you look at the income, so income could be like any kind of number. It can start from 1,000 or 100 or 200 or 5,000 or whatever. It can go up to any number. There's no fixed limit to it. But in case of cars, so how do we basically interpret what are the statistical representation of categorical variable? If you remember, we are doing something in Python on data when we are trying to figure out something like unique, how many unique numbers are there, what is the frequency variables, right? And we are trying to figure out the number of frequency of one particular, how many cars are there in this particular range or something like that. So basically we can do some kind of frequency distribution. We can understand it from the frequency point of view. So this is what essentially this idea is. So there are many ways we can essentially understand it. Let's say that there is some data point wherein you have these kind of cars, for an example, Audi, BMW, Mercedes. So one way, so let's say there are 335 data points. This is from the information of 335 people. Let's say 500 people. 500 people's information is there, out of which 335 people have given their information of the cars. So one way simply we can see is that what is the frequency of these cars. So this is one way of looking at it. Another way of looking at it could be like bar charts. What you can do is you can simply create bar charts out of this. So you go there. Right? So like this, we can do something like this. If you want to understand it visually, we can create some kind of bar charts, or if you want to simply understand it numerically. So there are two ways of understanding the data. One is visualization and one is numeric way of understanding it. So this is the frequency distribution simply, and this is the visual representation. It's just to get the understanding, okay, how many are general. So the visualization is a very powerful tool of understanding the data. We'll see it looking forward. Right now, we'll do most of the things in Excel today, just to give you a gist of all the statistical concepts we have. And later on, we'll also, maybe tomorrow, we'll also do a lot of plotting and how do we create graphs in Python. We'll see that visually. So today, for the understanding purpose, we'll use a lot of Excel sheet. So right now, what I've simply done is OD is like here. You can see the average amount. It will give you some sort of understanding of the average. So average is something around more than 100, 110, and like that. So this is one way of understanding it. So similarly, like I have created these kind of charts are available for this different kind of, how many sales have been there or something, like for Audi, BMW. Similarly, what you can do, other way of representing this categorical data is you can create a pie charts. The way we have created this, all of you have worked with Excel, right? I don't need to show all of these things, or do I need to? Anyone of you have not done any work on Excel? Is there anyone like that? Then I'll basically take it more, little slower. So that is what I'll do. Otherwise, I can simply speed up if you understand all these things. Anyone like that who has not done any work on Excel till now, or not drawn any charts or anything? Okay, so all of you have done something. So I would assume that I can go a little faster so that we can come to the statistical concepts. So similarly, we can do some kind of pie charts, simply understanding that so this is one way of. So what we are trying to understand right now is what are the various ways in which we can basically represent it, the categorical variables. So this is one way. You simply put the frequency chart of it, or you can put a relative frequency of it. Relative frequency is nothing but theoretically speaking, what is relative frequency? I'll show you. So this is the number we have for the frequency. So for each of the item, how it is going. So this is like this over sum of all this, which is essentially 135 only. So that's fine. This keyboard is. Okay, so this is essentially your for each of them, what is the percentage? That's what it is showing: 37%, 29%, and 34% out of the total. And that's how we can show it. Another way of showing it is that we can also show this OD and everything. And apart from that, we can also show something like the cumulative number, which adds up. This number will be 335, right? And you can show all these things separately. And so this kind of charts are called Pareto chart, wherein separate distribution also you show, and you can also show something on the cumulative front. So this is one way of representing the categorical variables. All right. And okay. So now what we are talking about is frequency distribution. So there can be many ways. Other than that, what you can do is for any data set, as we are talking in case of A's, we can create different A's buckets. Like in this case, this is simple data set. And if you put the pivot, all of them are like only once everything is there. So this is a data set. If you put the frequency distribution, everything is one. But now that doesn't make a lot of sense that everything is one. So you can create some kind of distributions, like you can have it in the interval of 1 to 5, 5 to 10, or 1 to 10, 1 to 20. Similarly, you can create some kind of distribution. Over here, what has been done is interval width has been created 20 and desired interval is 5. Let's say that total number of intervals. So total number of interval, if it is total number, if you want total number of interval as 5, then you have to and it is 100. From 1 to 100, so you can create 20 interval width like that. So it's just one example of it, very simple example. So we are creating it, starting interval, ending interval, and what is the frequency there. And then you can also create this relative frequency. So this number will add up to 40. So this is how similar things we can do for all the variables which are continuous, but we want to convert them to some kind of categorical variable. So we can do frequency distribution like this. So this is one way of representing it. Simple enough. Now, for categorical variables, there is one more way of representing, which is called histograms, right? Histograms again are nothing but your hello. Yeah, histograms are nothing but essentially what we are trying to do is just on the charts, like we have done it for bar charts in this case. We can simply do a histogram, and which will give us this kind of clue, like in whatever interval, like 1 to 20, 1 to 21 interval, how many are there. So this is one good way of basically looking at the data set. So this is what it gives us about a clue, like how the data set looks like. So in this way, it gives us kind of understanding. So what we're trying to do is just trying to understand the data both from the point of numeric point of view and a visual point of view. I'm not going to too many details of all these things because I would assume some understanding you would have about all, because this is very much high school mathematics. So I'm just trying to quickly cover all of this. Any questions you have with the histograms or any relative frequency, anyone? Or how do we, and it's very simple to basically create all these things. Like if you have not done it in Excel, though Excel will not prefer as much. So by default, it is given as this, but we can always build. For an example, let's say this is a data set, we can quickly go through it. So by default, it has given us 3, like 1 from 39 to 77, 77 to 75. And you can create your own intervals. Like let's say you want 5 intervals, so you can create like this. So all these things are available in charts, and we are going to do all of them in Python also. But for now, because in Python, we may not have this kind of visual capabilities, like it becomes a little difficult to see it there this way. So I'm just using Excel for now for understanding all these things. Okay. Now, let's say that we want to see for different, like in this case, it is about the information that how many stocks, bonds, and real estate, investments are done by different kind of investor, investor A, investor B, investor C. So one good way of looking at it is in the form of, bar charts like this. So you simply put all the information here, and a bar chart is a very good indicator that how these investors are basically following it. So how many, how many stocks are taken by investor A, how many bonds are taken by investor A, and how many real estate. So this gives us a very clear understanding of what is happening in this. And another part of it is from the storyboarding point of view as well. Because a lot of times what you will be doing is, once you have done some analysis or something, that it's not always good, it's not a good practice, in fact, to show all the times these numbers. If something is in comparative state, it's better to show it in form of graphs. So this is the way we can create some kind of bar charts. Like, like this, you can essentially create all these bar charts like that. So in Excel also, it's very simple. We'll see it in Python also, using some commands. We can do it very easily. So this data is from one of the SAT scores. So of a person, how much he is scored in reading and how much he is scored in writing. So another one way of looking. So basically, what we're trying to do here is we're plotting a scatter plot. A scatter plot essentially gives only between, like, let's say that right now only two variables are there, reading and writing. A scatter plot will plot a lot during our modeling techniques also. That it will simply give, like, in two dimensions, reading and writing, how the person has done in reading and writing both. So do you see there is some kind of relationship between reading and writing? Is there a kind of correlation? Do you find any correlation between it? Simply, it has been plotted. Only two numbers are there. It's like simply plotting these things on two-dimensional graph. This is what this scatter plot is. There is nothing has been done. Only points have been plotted. That is what a scatter plot is. So this is another. So a scatter plot is not used for categorical variables. Scatter plot will be used for continuous variables all the time. Or for any variables, it can be like, let's say that age and something that can also be used, but it is mostly used for numeric numbers only. So can we see? So important thing is not just these graphs. Important thing is the interpretation of these graphs. So here, can you see any correlation between reading and writing? Is there any correlation? Do you find by looking at the graph? Hello?
Yeah, hi, this is Sam. I think it's linear, right?
Yeah, so just by looking at the graph, what we are seeing is that as the reading score increases, kind of, writing score is also increasing, right? Whenever the, like, let's say that in this case, reading and writing scores are high, over here, reading and writing scores are both low. So sort of, for the person, if he has competence of reading, there is a possibility that he has a competence of writing also. So that is what it is essentially showing, that reading and writing increases continuously. That is what it means. It has a very kind of one-sided relationship. It's kind of a linear relationship. So these kind of interpretations we can draw from all these numbers. And this is, in fact, this is the basic of this correlation, is the basis of linear regression per se. So which will have a lot of stuff, which we'll talk about causality over there. So this is not a causality. It does not imply that someone is able to read it. Will imply essentially that he's able to write, right? Because many people can speak. Let's say that speaking and writing. Someone may speak something, but it's not necessary that will lead to writing. That there can be many cases. We can understand one language, we can speak one language, but may not always be able to write that language. So that is a possibility. So there is something called as correlation, and there is something called as causation. So over here, there is a kind of correlation that is very much definite between these two variables. There is a kind of correlation that person who is capable of reading is also capable of writing. Generally, that's what we are seeing here. So this is how we need to interpret, and interpretation, because it's very simple to draw these graphs, but interpretation becomes very important for a data scientist. Now we'll look at few more things here. Okay. Now, what we'll do is, so in the from a statistical point of view, there are three parameters essentially. One is central tendency of the data. Then dispersive tendency of the data. Dispersion tendency of the data. And then variation tendency of the data. Now, any data will have all these kind of parameters. Let's say that I simply write a random number over here. Let's say I just put some random number between 1 to 1000. Okay. Few numbers I have just taken. All right. So let's just calculate simply the mean of this number. Right. So average is 498. Now the average is 498. Let's say that this is my average number. Maximum and minimum. So maximum would be somewhere from this data. Obviously, it will be less than 1000 because we have put the 1000 limit, but let's see. So 974 is the maximum and minimum is 57. So what essentially it means is that 498 is the average, 57 is the minimum value, 974 is the maximum value. So if you look at it, this 498 is quite far off from 974 and it's quite far off from 57 also. So there is a kind of distancing between the numbers. So if we have to just tell few numbers, which will essentially, like right now in this, there are many numbers. There are 27 numbers in this. But then if you have to just give some sort of summary of this, we cannot just say the average of this number is 498 because it will mean that what exactly the number contains, we cannot have good view of that. But then let's say that we are talking that, okay, this is a minimum number, this is a maximum number, or this is a standard deviation. So it will also give the view of the data in a larger sense, that how the numbers is essentially look like. So that way, average is one way, which basically tells you that, okay, what is a central figure? What is a central number in all these data points? So average is one of the parameters. So we'll just look at some of these central tendencies here. So for an example, the central tendencies are like three central tendencies are there generally: mean, median, and mode. So what is a mean number? Mean number, mathematically is just the sum of all the numbers and divided by total number of accounts. So for an example, let's say in the New York City, we take the mean of all this. So the average comes out to be 11. So this is what it is. Median in mathematics is defined as if you sort all these numbers in ascending or descending order. Like right now it is sorted in ascending number. And whatever comes in the middle, right? So if there are 11 numbers in this, so middle point will be sixth number. So whatever this sixth number is, so that is called the median. So basically all these things as we're talking about, this is central tendency of the data, which essentially points toward some of the central value or the point at the center. So median also becomes one of the central tendencies. So 6 is the median for this number. All right. So median of this is, we can use a function, or you can simply look at it that 6 becomes the median of the number. Similarly, what is a mode? Mode is a number like whichever number is repeating maximum number of times. Whichever number is repeating the maximum number of times, that is called mode. So in this case, what we can see is 3 is getting repeated maximum number of times, right? 3 is coming 2 times, everything is 1 is just 1 time. So that becomes the mode. So it also gives you, like, let's say that there are some numbers between 1 to 100, and 54 is coming, let's say, that 20 times out of 100 times. So it means that there is a good possibility that number is something around 54, because most of the number is representative of that. Now for this particular variable, similarly we can take the mean, similarly we can take the median. Median in this case would be like, let's say that there are only 10 numbers, so median will be average of 5th and 6th, which is like 4 plus 9, or sorry, 5th and 6th is 5 plus 6 by 2, which is 5.5. So that is what, so in this case mean is also 5.5, median is also 5.5, but there will be no mode, because all these numbers are just 1. So there is no such number which is like maximum number of times. So all these things it gives a central view of all the data points. So one thing that we must remember here is, one number is not sufficient enough. Neither the mean nor the median nor the mode is sufficient enough to give the complete picture of it. We can get a better understanding of the data point by just looking at all these numbers. In this case, what we are seeing, that mean is something around 11, median is 6. What is happening now is, if you look at this data, right? So mean is 6, sorry, median is 6 and mean is 11. So this data is more skewed towards larger number. Like we can see here, one is 11 and another is 66. So the data is more, so on a number line. Okay. So on a number line, let's say this starts from whatever, where number, let's say this is 0 and this is 100. Okay. I don't have that pen, otherwise it's okay. So now in this particular example, what is happening is, the mean comes out to be 11 and median is coming out to be 6. So basically median somewhere is, this is how the data looks like. Essentially it means that this number is coming out to be the largest number that was there, which is 66. This is not coming good, but I'm just trying to show you something. That this median is here and mean is somewhere here, which is 11 and median is 6. So mean is greater than median. So basically there is some kind of a skewness in the data. Data is not very central. So we'll see that another parameter that we need to look at apart from mean, median, mode, it's some kind of, dispersive tendency of the data, which will give us this kind of parameters, whether the data is skewed or not skewed. So for that, we'll come to in this, we'll learn about something called skewness, what we are just trying to see. So in this data points, let's say that this is a data point. Now in this data point, we have 3 tendencies which we have just seen, mean, median and mode, right? Mean, median is 2.79, median is 2 and mode is 2.0. So similarly, other data sets are also there. Few of them, just a few numbers. Okay, in one of the cases, the mean is greater than the median. In another case, mean is less than the median. Mean is 4.9, median is 5. And in this case, mean is equal to median for this particular data set, if you look at it. All right. So now, when we plot this, now what we have done is we have just created some intervals here, simple intervals just to plot histograms, just to get the whatever I was trying to show you through this chart. In this case, we'll see using histogram. So in this case, what is happening is the maximum value is 7, minimum value is 1, right? So a skewness is a parameter which will basically tell you. So what we have done now is we have just plotted a histogram for this number, all these parameters. What we are saying is that maximum number is coming in between 0 and 1. 0 and 1 is like 4, 1 to 2 is 6. So obviously, because smaller numbers are on the maximum, so basically the frequency of a smaller numbers are quite great. Like it is much bigger, 6, 4, 4, and larger numbers are very small. So what will happen is that mean will mostly shift. Median will be somewhere in the middle, but mean will shift towards right hand side because some of the numbers are very high, and that is what is happening here in 2.7. Nice. So what we are saying is that most of the numbers are on this side. So the graph somewhere becomes like this. So this is a positive skew where the tail is towards the positive end. So this is what is called as skewness. It will, and we can also find this by a simple function called skewness. And we'll see that the skewness will be positive in this case. You can see it here, right? The skewness is positive. So positive skewness means the tail is shifting towards right hand side, which also means, right now we have just seen from the very small data set, but which also means if the number is very high, let's say that the skewness number is quite high, it means that tail will be somewhere very long down the line. This means that there could be some of the outliers towards the end. If the skewness is very, let's say in this case, the skewness is 0. You can see it from the graph also. It's quite very normal kind of graph, that whatever is on the left side, similar kind of distribution is on the right hand side. So there is no skew per se in this, and we can see it, the skewness in this data. It comes out to be 0, right? So there is no skewness. This data is completely normally distributed. So our work would be in a way for data preparation to make data as non-skew as possible. So basically skewness should be as close to 0 as possible for most of the variables. It will not be exactly 0, right? In this case, it's completely normally distributed. Everything is perfect. But it should be as close to 0 as possible because that will make our data more evenly distributed. And that is one of the role of data preparation is. So we always have to check whether the data is skewed or not. Okay, in this case, we are seeing completely. So in case of 0 skewness, it will be mean is equal to median is equal to mode. That is what it will happen if the skewness is 0 for the data. And that is what is in this particular data we are seeing. And similarly, if the skewness is negative, which means the tail will be towards the left. So basically your mean will in that case will shift towards the left because most of the data points are, some of the data points are on this side. So I'll just calculate the skewness for this. Which you can see is minus 7.8. So minus means that tail is on the left side. Negative skewness, the tail is on the left side. So there are few numbers which were quite on the left side compared to most of the numbers. That is what this distribution will give you. So skewness becomes another important parameter to have a look. Any doubts here? See, what we are trying to do is we are not getting into too many mathematics of it. We can also look at I'll just show you something for now. So see, this is negative skew and positive skew, and one thing is there are many ways to calculate skewness. So like in this case, is Pearson moment of skewness. Like this, there can be formula. All the time there can be, obviously, whatever we are calculating for mean, there is a formula. For median, there is a formula. For skewness, there is a formula. We are not getting into too much of a mathematical side of it, like how this is calculated. In this case, it is essentially trying to show you. So basically, skewness, if you look at it, we'll just do it from the intuition side for now. That whatever number is there from the mean, we'll divide it, and standard deviation, basically we'll subtract it from the mean and divide by the standard deviation. And then all these plots are created. So we'll not get in for everything. We are not getting into the mathematics of it. We'll just understand that how it is basically helping us. So formula wise, this is what the formula would look like. But for us, the important thing is because we have the functions. We don't have to get into formula because of the reasons, because we have the functions. So the thing is of the interpretation, that whether we are able to interpret, because skewness is something we will use for outlier treatment. Whether there is an outlier or not, for that we need an understanding of the skewness. That is our whole objective as far as data science is concerned in this particular course. So any doubts till now? What is a skewness? Similarly, there is a parameter called kurtosis, which essentially gives you how how sharply the data is falling. That is also another distributor for this. Any questions in this skewness?
So simply, what do you mean skew?
Okay.
Yeah.
So see, skew means the data is basically, see, what we are trying to tell you is, this is a data point, right? What we have in the simplest of terms, this is my data, right? Simple one data you take, okay? Now, if you take the frequency distribution of this data, 0 to 1, 1 to 2, 2 to 4, 67, how many numbers are there in this? So if you look at it, 0 and 1, so basically only 1, there are 4 numbers here, right? You see this point? 4?
Yeah, right. Yeah.
Okay, similarly like 2, so this is the frequency distribution. 2 is coming 6 times, so that is what we are looking at. 2 is 6 times, right?
Okay.
2 to 3 is, so essentially this is what 4 times is. Now what we have done is, we have simply done a plot for this.
Okay, interval versus frequency.
Yeah, so what we have done is, what we have done is, we have simply plotted this number 0 to 1, 2, 1 to 2, 2 to 3, 4 to 5, 6 to 7 in this case, like, so all these numbers are plotted. Now what you say is that if you simply look at this, so most of the numbers are seem to be concentrated on this side, and only few numbers are concentrated on this side, right?
Yeah.
On the left hand side, most of the numbers are concentrated. On the right hand side, only few numbers are concentrated. So
Okay.
the data is more, so basically there is a tail towards this right hand side. And when the tail is towards right hand side, that is what we are calling as skewness. In this case, if you look at it, this data point, so there is no tail per se, right? This is very, this data is quite, so this is about symmetry. It is essentially telling you whether the data is symmetrical or not. And we are always concerned with the symmetrical data points. So in this case, you look at it, if you just see it from this perspective, it's very symmetrical data.
Okay.
You're getting my point?
Yeah.
So that is what is skewness. If the data is not symmetric, it means that there is a skewness in that data. Okay?
Yeah.
So this is another parameter that we look at. So another thing that we need to look at is, actually there are too many files. Let me just close all these files. Okay, so now what we'll look at is something called as variance. As we're talking about the data, we'll have some kind of variance associated with it. So what do we mean by variance is, okay, very simply, let's try to understand variance. See, the average of all these numbers that we had just written is 498, right? But this 498, if you look at it, is different from okay. So this is my average number. So variance essentially tells you that how different is the average number from each of the numbers of the data set. So 498 is the difference of, 498 is the average of all these numbers. In this case, let's say that the difference, if we just, and this is my average number of the data set. So we can have the look at difference, right? Let's say how different is the data set from the mean. So for an example, this is my average number and this is the digit here, right? So what is happening is, if you look at it, we have calculated the average, but each of the number is somewhere different from this average number. So in a way, what we need to understand about the data is how the average, how much the average is essentially varying from the actual number. So right now we have just calculated the difference, but then difference itself will not give us clear picture of as to what is happening. So what we also need to understand is, see, and difference can also be positive and negative. As in this case, this number is far off from there and average is less, so the difference is negative. Similarly, this number is 342 is on the left side of this, and this is 498. It means that 156 is a positive number. But when we are talking about like general average variation, then positive and negative doesn't matter much. We just have to see that if the variance is quite high, it means the data is widely distributed. The data is not evenly kind of distributed. So this is what this number is essentially telling us. If you look at this variance formula, so xi is the number. Like in this case, all these things become xi. Okay, the actual numbers, and this is a mean. Now what we'll do is, let's say that if you simply square all the numbers, squaring all the numbers, what if you put some power to a number? Mathematically, if you put any power to the number, let's say that I'm just putting difference square, so it will exaggerate or expand the value itself. It will basically make it more, it will give us more expanded view of whatever is happening. So in this case, if I simply put the square of this, now for all the numbers, what I have done is it has given us a square. And if you look at the formula, it will tell you if you sum of all the squares and divide it by the total number. So this gives you the variance of this number. So essentially the variance becomes sum of all these numbers divided by total . Right? So the variance in this case becomes 70,769. Now this is just a number, and variance will always be positive because we are always doing the squares of the number. But the problem now is we understand that mean is, let's say that mean is 498. the average number is 498. Variance of the data is 70,769. The problem here is we don't still get any information that what has happened exactly, because all these things, let's say that if this was some kind of let's say unit, I put simply as kg. It was representative of some kind of mass. So everything is kg in this case. Okay, so everything is kg, kilogram in this case. But now let's have a look at this number. What we have done is we have squared all the numbers. So so for the variance, the unit would be kilogram square, right? So the unit becomes here kilogram square. We cannot exactly, and this mean will be in the average of kilogram again. So we cannot simply, like let's say that there are two things. My height is, let's say 6 feet, and someone else's height is 5 feet. So 6 feet and 5 feet can be compared, that what is large and what is not large. But if I say 36 feet square and 5 feet, so that cannot be directly compared, right? You're getting my point. So over here, the problem with the variance is that it gives us the understanding, okay, there is some kind of variance in the data, but what that variance is, so that we don't get to the level of understanding with this kind of, because everything is in the range of between 1 to 1,000, but this number becomes very, very exaggerated number, which is 70,000. So what we could do is, because this is kilogram square, or unit becomes a squared, unit is squared. So what we can do is we can simply take the square root of this number. Now, a square root of this number is very much comparable to our general data set. Like all these general data sets are in the range of 600, 500, 200, 300. And this number is also in this range of like similar kind of range, because we have simply done the squaring root of variance, right? So this is called standard deviation. So all our comparisons are going to be based on this standard deviation, which is the square root of this number, a square root of the variance. Because with the variance, we cannot get the right picture of the data, but standard deviation gives us very good picture. But what picture we are going to get is, as I was trying to tell you, that all the numbers, like let's say that there are some numbers, mean is here, and if the data point is here, means the variance would be very less. As we can see some of the cases, wherever the number is close to 498, like in this case, if you look at it, right, it's 440. Very close. So in this case, the variance is quite less compared to if it is quite very, very high. So that is what this number is basically denoting. If the difference is very less, the variance will be less. If the difference is high, variance will be high. And that is what we are basically trying to sort for. Whether the data is, if the average number is too far off from the actual number, or average number is too close to the actual number. So that is what we are trying to look at. And a standard deviation gives us that picture. Okay, so now there are a couple of things. We have just seen how this variance. So basically there is a formula, simple formula you can use VAR. Now with the variance, if you look at it, there are a couple of formulas. One is VARS and one is VARP. So what this S and P is, we'll just quickly understand this thing. So there is something called as population, and then there is something called as sample. Okay, so for now we are in our cases, what we are trying to look at is just a smaller number, only 5 digits, 10 digits, 20 digits. Right now, that's what we have encountered. But in practical scenario, what will happen is, let's say that there are 1 million records. We have information of 1 million or 10 million customers, right? So for 10 million customers, when you have the information of 10 million customers, not all the time for any purpose we are going to use all the 10 million data points. Maybe we'll just figure out, let's say that something, maybe 10% data point or 5% data points, which may be like, let's say 0.5 million. Okay. We create one smaller subset of the data. So 10 million was the complete population. We have just created one small set of the data, which is 0. Because what will happen if you use a lot of data, a very big data point, then computation becomes very difficult and it takes a lot of time also sometimes. So we don't want to get into those kind of situations, and we just take a subset of that population or a sample of that population. So whenever you are taking the sample of the population, and every sample will be different. Like let's say, in this data itself, there are some 26 data points, right? 20 or whatever, 23 data, 27 data points. Now I can simply take any number of, let's say that I want to pick 10 different points from here. So I can take these 10 points, any random I am simply choosing, right? Or I can take any of this point, whatever. There can be many possibilities of choosing 10 points from there. So you can essentially choose any number of points. Like this is just a population of 27 points, and I am choosing a random 10 points from there, any random 10 points. So for all these points, right, for all these 10 points, there will be some mean. So let's say, what is the mean of this number? Okay, so mean of this data is 594. Okay, similarly, we can simply, we have just taken 3 samples from this data set. So if you look at it, all these samples are randomly selected. All of them are between 100 and whatever this number. From this data only we have selected this. For all of them, the average number is different. For all of this, median will also be different. All other numbers, standard deviation will also be different if you look at it. Okay, so you see over here the average number was 489 over, and average is 266. Now I am just selecting some random points from this data set for which the average is also different and standard deviation is also different. But when we are taking a sample, so what we are trying to see is, or what we are trying to essentially say is that this sample is a right representative of the population. Now tell me one thing. For the population, this is for the population, right? This is the average of the population, 498 and this. So average of the population is 498. Standard deviation of the population is what we have calculated here, 266. This is the standard deviation of the population, fine? And similarly, we have taken 3 samples, S1, S2, S3. For these 3 samples, these are the means and standard deviations. This is the mean, this is a standard deviation. Now you tell me which of the samples is very close to this population. Hello, are you getting the question? This is for the population. Okay, and these are for the samples. We have just taken some random samples. All right, simple some random samples, 3 samples we have taken of 10 numbers. For that, these are the average and these are the standard deviation. For the population, this is the average and this is the standard deviation. Now, can you tell me out of these samples, which is the most right representative of the population? From these S1, S2, S3, which is the most closest to the population? Most right representative of the population. Hello? Can you see the screen properly? Hello?
Yeah, Austin, we can see that.
Yeah. So I was saying that we have a population. You understood the question, is it?
Yeah, I got the question.
S2 is the nearest one to the population.
So S2 looks like the nearest one, right? Because this has the, see, first all of you, because I don't know, because you're not responding, so I don't know whether you're getting or not getting. What we have done is we have just selected some numbers between 100, between whatever 100 and 1000, right? So that has become a population. There are 27 digits in that we have seen. This is the number. Now from that we are just taking some sample, because why I'm taking this example with some smaller numbers, because when you're doing it on this larger data set, you'll always be working with the samples. You're not going to work with the population, because many a time we don't have the information about the population also. We just have the information of the samples. Okay. So when we are talking about the samples, and when we're talking, because what has happened here is, right now we understand that average is 498. In this case, average is 467. So quite near, not that far off. But this is quite far off. 594 or 568 is very different from the population average. Similarly, standard deviation is 289. This is 245, and this is 319. So this and this is quite close. So obviously, sample 2 looks like most correct representative of the population. This is what it looks like, right?
Yeah.
Okay. So now just think of a situation as far as the sampling is concerned. Let's say this coronavirus situation is happening in COVID-19. Right now, the case has gone up to some number. I think, what is the recent number? Do you have any idea worldwide? Okay, so
1
let's
crore
say
40 lakhs.
So how much? Sorry.
1 crore 40 lakhs.
Okay, 1 crore 40 lakhs is what is the number, right? 1.4 crores. Now let's say that someone, now there are various drugs development is happening, right? Many, many companies, many institutions, many laboratories, many scientists are basically trying to figure out some vaccines or drugs for this virus. Now, what will happen, though there are 1.4 crore population which has been affected by this virus, but imagine if you have to create something, if you're trying to formulate a drug or formulate a vaccine, you cannot obviously use 1.4 crore people to test it on. That's not possible, right? Because they can be in any corners of the world, and we don't know information about all those 1.4 crore people. We don't have information about all their health background, all the communities, all the different kind of geographical background. We don't know information about all of them. So 1.4 crore is a big number in that sense. But someone, let's say that in some United States, some laboratory or some scientists are preparing some vaccine. They can definitely, what they can do is, possibly not on 1.4 crore people, but definitely on 4,000 people, they can do some tests if they are preparing for some vaccines. Hello.
Yeah, makes sense.
Right? Makes sense, right? 4,000 people, they can check whether it's working or not working.
Yeah.
So now this 4,000 in a way has to be because if you have prepared a vaccine and you have told to the World Health Organization and it has been approved clinically, everything has happened, it means that in a way, they have to be somewhere sure that this 4,000 is basically a correct representative of all the population in a way. Then only you can basically prescribe that drug to anyone else. Make sense?
Yeah, yeah.
Right? So that is what I am trying to say, that we may not have the information of 1.4 crore people, but we can definitely have information of some number of people. So this is just a 4,000 would just be a sample, or 1,000 would just be a sample. Will that be a good representative of the whole population? That we'll see. There are many ways of doing it. One thing is, we as a data scientist, we need to look at it from the statistical point of view. But when you are collecting the data, or someone who is doing the data collection, they may have to check it from different kind of views. Like let's say that someone is in United States, which becomes either in North America or South Africa, which is on a different, which is altogether a different continent compared to the eastern side of the globe, which has like Southeast Asia or Indian subcontinent or these kind of areas, or you may have African subcontinent. So when you are doing the sampling, when you are picking out the sample of 4,000 people, what you could also do is you can basically take the samples, because all these samples are collected and sent for various verifications. So you can have these samples for all different subcontinents. That will make it more stratified sampling, right? Just a simple thought process I am trying to give you. you take the data from all the 7 continents, some data points like 400, 500, you take from all the continents, that's not just limited to South America. So in that way, if you look at it, it is a holistic view. It gives a much more larger perspective whether a drug will actually work on different kind of population or not work on that population, right? Make sense? Because people in different regions will have different kind of, affinity or response to a vaccine. That is very much possible, right? Hello.
Yeah.
So that's the whole thing about sampling, that you can not always have work, you cannot always work with the population, but you can work with the sample. So what we need to understand is, statistically, we need to understand whether this sample is a correct representative of the population. So for a data scientist, what is the important question is whether the sample with which we are working is correct representative of the population. Okay, so this is a very important question for a data scientist, because I have given you in context of what the coronavirus, but this is something we are going to see in our examples also. When the data set is quite large, we'll not work on the data rather than we'll work on the sample. So whenever you are working with the samples, so the definition becomes little different for whenever you're talking about the, like in this case, the, and that is why all this formula becomes different. The statistically formula for a sample is different, and is statistically the formula for population is different. Okay, because it's just a subset. So statistical definitions have been created differently. Some variations based on the number of records that are there in that. So that is why these two formula are different. Like if you look at it, standard deviation of the sample or a standard deviation of the population. So if you think it is a sample that you're working with, like in this case 4,000 will be a sample, so you go with the standard deviation of the sample formula. The formula is not very different. In some of the cases it's quite different, but in some of the cases some of the parameters is not that different. That's why sometimes we may be using population, and sometimes we'll be using standard deviation of the sample depending upon what data we are encountering. Am I clear?
Yes.
Okay. Okay, so that is what it is. So it is trying to do. So this is the, let's say that in this case, this is simple population, and the population formula that is, variance formula that is being used is variation dot population. For population, what is the variance, and that formula is being used here to calculate the variance. But because now you have taken just 5 things from here, from this particular data set, this is a population. From this, you are taking a sample. So rather than calling it population, let's say it's called sample. Okay, so the sample variance becomes little different, which is, this is a sample variance because you are using a sample of it. The formula even statistically is not much different. It's just that in this case you will be taking that number of samples minus 1. In this case it's number of samples. So we'll not get into mathematics of it. We'll just understand it, why this is happening and how it is happening intuitively, more of it. Similarly, if you look at the population variance, so this is a population. The population becomes this. So this is a population variance. Similarly, standard deviation also would be changed. Now from variance, so this is a variance. The problem that we are trying to look at, as I told you, if it is in like the variance will take the squares of the number, and it will never be in negative because it's always a squared. It basically exaggerates or expands the number a lot. So what we look at, the standard deviation, and that is what this example is trying to tell, with some like with some units also. So this is a unit. Now let's see what this thing is doing. So this is a pizza price. Pizza price for different for different situations. These are the pizza prices. the price is same, right? One is in pesos and one is in New York dollars. So basically American dollars and pesos. What we are trying to see here is, let's say that these are the pizza prices in dollars, and in the same, it's basically just a conversion. Okay, there is nothing here. It's just that the numbers are converted into pesos. That is all this is, right? Now, let's look at so basically both the things should mean essentially the same. It's just the unit change that is there. It's just the unit change, but actually from the actual perspective, both the things are same. There's no difference. I can say that I am either 180 feet or 180 centimeter, or I can say I am 6 feet almost. So both the things mean the same, but numerically 180 is much larger than 6. We are getting my point. That is why this all difference is created. This 18.8 is far more greater than numerically 1. So that is why this our variance will not give us a very good picture. As you can see, in this case, the mean is 5.5, which is fine enough. This is a mean of the number, and this is a mean of the pesos. This is a mean of all the pesos. Variance we can calculate. Variance, simple variance we can calculate using the variance formula, and you would see that variance in this case is 10.72, and in this case the variance is 3793, because the numbers itself are so large and it gets even more exaggerated by squaring, and that's why this variance is very high. But the problem now that is there is, with these two things you cannot get anything, and as I told you, this will also get squared. This is dollar and this is dollar square, so we cannot compare what is this dollar and what is this dollar square. But then if you take the standard deviation of the number, so this is my 5, and the standard deviation is essentially tell you that there's a difference of 3, right? So generally the numbers which are available in this will have a general standard deviation of 3.27, and it is in the same units also. So this makes my job much more easier to read this data point. Similarly, if you look at it, this MXN 103 is the average and 61 is the standard deviation. But 3793 will not solve for us because it will not make any, I mean, we cannot basically intuitively, we cannot understand it. This has a mathematical significance, but intuitively we cannot understand anything from what is this 3793 and 103. But over here, 103 and 61 is quite comparable. So which gives us much more clear understanding. So there are two things that becomes very important for us. One is mean and standard deviation. So these two parameters become very important for us in understanding any particular variable. Now, another thing that you can look at, let's say that if you want to compare these two things, New York dollars and pesos, okay? If you want to compare these two things which have different units and the numbers numerically also they are different. So how do we basically check whether these two things are the same thing or not, whether they are giving the same picture or not? So obviously with the mean also we cannot get that two number because mean here is 5, pesos is 1.3 or 103. Standard deviation also is not a representative of that because it's only giving you 3.27 and this is 61, which is quite different. So basically we cannot say. Then we may think, okay, these two things are completely different things, but that's not the case actually. But if you calculate something called as coefficient of standard deviation or coefficient of variation, so if you calculate this coefficient, then it will help you compare two different things. These two things with two different units, you can very easily compare them. So how do we define this coefficient is essentially a standard deviation over the mean. So if you calculate the standard deviation over the mean, which will give you that how different these two things are in relative context. And when you're taking the relativity of it, so all these unit factors will get cancelled. Because if they represent the same numbers, then their standard deviation in their numeric thing will be similar to standard deviation in the New York dollar numeric numbers. And that will be very clearly defined by this thing, coefficient, which is standard deviation by mean. So if you want to compare two things, then you will always be looking at the coefficient of the variation. How the variation, so this is called coefficient of the variation, and this will not have any units, because if you divide this 3.27 by 5.5 and dollar gets cancelled, so only a numeric number, a ratio will come, and this will help us get to the core of whether these two numbers are comparable or not. So that So this is one very important, the coefficient of variation becomes another very important parameter. Any questions still here? Do you get this, why we need this coefficient of variation?
Yeah, Austin.
Yes, it's a simple mathematical problem.
Yeah, it's just a mathematical thing of comparing whether if the two units are different, whether they are representing the same thing or not. So this is one way of doing it. There are other ways we can simply do some kind of a scaling. So this is also kind of a scaling only to understand it. But there are more, little more advanced stuffs like in clustering and all. We'll see we'll scale the data on similar standard deviation because the parameter will remain the same. It will make the standard deviation and mean constant. If you put the data, then everything, then whatever the parameters, like let's say that number of credit cards, as I was giving the example, the number of credit cards could be 0, 1, 2, 3, 4. Age could be something 10, 20, 30, 40, 50. Or let's say income. So income could be in the range of 10,000, 50,000, 20,000. So for an example, let's say you have some variables like income, number of credit cards, or maybe whatever age for some people, right? These kind of parameters you have for some customers or some students or some employees, whatever, right? Employee 1, employee 2, employee 3. Now, based on this, you want to, come to some kind of conclusion that you want to sort of create some kind of groups for these people. Now, just imagine if you compare like credit card, which is like, let's say someone has credit card number 3, but the income is $30,000. So 30,000 and 3, if you look at it numerically, then 3 will get nullified in front of 30,000. You are getting my point? It won't make any sense. Let's say that age is 25 and income is 30,000. So both these things will not have. So if you are using all these 3 parameters to get into to create that sense of grouping, then mathematically this will all nullify all these numbers. But then credit card has a value, age is a value. If someone has some children or anything for that information, any kind of information will have some value. So if we are standardizing it in some scale, like what we are doing here, dividing it by standard deviation by mean. So in those cases, we can definitely use mean and standard deviation will become very, very imperative. Okay, so that everything, like let's say that in this case, if we put everything between the range of 0 to 1, that this number also somehow becomes, let's say 0.3, and this number also become, instead of 3, it becomes something around minus 0.1. So all these things will become, very similar. So in that case, mathematically there won't be any difference. But as we have seen that they are different in actual sense, but mathematically they won't have any difference. So we can use all of these numbers to create a group or whatever we want to do with those numbers. So that is what will happen. And we'll see, because over there mean and standard deviation will become very important. All right. Any questions till now to whatever we have covered?
No, so far good.
Okay, so let's take a break of 10, 15 minutes. It's 21:30 almost. So we'll begin at 21:45 from this. Okay, after 15 minutes.
Thank you.
Okay. Hello. Hello.
Yeah.
Yes, Austin.
Yes.
Okay. All of you are there. Okay. All of you are there. So, okay. So till now, whatever we have been doing, as we had seen on that, there is something just for one data set. Right now, we have just seen whatever, be it central tendencies or dispersive tendencies or variations like variance, standard deviation. They have just been applicable on one of the data points, like only one series, like if it is size or if it is price or if it is or it is income, whatever. For one particular variable, we have this all these. So they are called type of univariates. If you are doing some kind of univariate analysis, so those are the things you will do generally. You get into descriptive statistics of one variable. You get into you want to check the variance, you want to check the standard deviation, how things do some visualization and understand the data. Now, what we need also to understand is relationships between two variables, right? So when I'm talking about relationships between two variables, so like if one thing is dependent upon another thing, we can have some kind of sense. Like let's say that the price, in this case we have some housing data, but for an example, price of a house, right? Price of a house would be directly proportional to the size of the house. That makes sense?
Yes.
So there is a kind of, direct relationship that we see. So as the size of the, the area or square feet area of the house increases, the price of the house is also most likely will increase, right? That is how if it is given all other parameters constant, like the area or the geography where it is located, all these things, if they are constant, simply based on these two parameters, it will increase. So there is kind of a direct relationship between these two things. So when you are trying to see that, how these two parameters, so one way of understanding how these two things are correlated, how two variables are correlated. So we have a parameter called covariance, as we had for one thing, which is called variance, that how the data set within is varying. We want to see that how the relationship between two variables are there. If there is any kind of if there is any kind of relationship between them. So covariance is one of the parameters we can have a look at. Okay, so covariance in a way will give us a sense of direction. So mathematically, the formula of covariance is like this. As you can see that this is a formula for population and sample. So there's not much of a difference with the sample formula. As I was telling you, in most of the cases when you are using sample formula, it will be n minus 1, which is a sample size minus 1. In this case, it will be sample. So we'll focus on this. That when we are talking about the variance and we're trying to calculate the variance of the numbers, we'll again use the same thing. How different the mean of one particular variable, as in this case, it could be like how different the mean of all these numbers. The mean here is 866. How different it is from there, and you multiply this with this. So basically, this is what is being done. In this case, if you look at it, 650 minus this, similarly this into this. So you are getting a multiplication of these two numbers, and when you're multiplying it, it again means that you will get a square of, or basically both these things, fit and dollar, will be multiplied. So it will have a kind of exaggerated effect on this, right? Because two numbers are getting multiplied, and so it will exaggerate the effect. But then this is how we'll calculate the variance, that whether two covariance, whether two numbers are located, and then you will divide it by the total number of elements in that population or the sample, that whatever you are considering. In this case, let's say this is a size, so we'll consider a simple sample size. So we are simply multiplying all these numbers, and for all of them, this number is multiplied. If you take the sum of this, so in the formula you have seen all these numbers are basically added up. It's the summation. So you take the sum of all these numbers, and you can see this number is 13 lakh, whatever this number, 13 crore, 39 lakh, 65,000. So this is a very big number, as I was telling you, because what is happening is you're multiplying these two numbers and you're trying to make, and the sample size is 5. So this you divide it by this number, G11, which is the sum of all these summations, and you come to this number. So this will give you a covariance of the sample. So this is a sample that we are using. Now, the thing is, with this covariance, again, we cannot have much of a sense that what actually is happening. And the problem is that we have a size and we have price. Okay, this is understandable. But this covariance number itself, like if you look at this 3 crore 34 lakhs 91,250. So it essentially, I mean, we cannot get much sense of what this number is representing. We can have a look at the plot, that whether on the size the price is increasing. So generally we are seeing that whenever the size is small, the price is small. So scatter plot is giving us that information. If you plot these two numbers simply, that the size is dependent of, price is dependent upon the size. So this number, but then covariation per se is giving some inference. What it is giving is, it is giving a sense of direction. If this number is, let's say, greater than 0, if this covariance number, in this case, as we are seeing, if it is greater than 0, then there is a kind of positive correlation, direction, or both of them are directly proportional. That would be a more appropriate to say, that both of these variables are directly proportional. That price is directly proportional to the size if the covariance is 0. If covariance is greater than 0. If covariance is equal to 0, it would mean that there is no relationship. Essentially, there is no relationship between these two variables, or they are independent variables. I mean, like, let's say for an example, if I have to say price of car or price of house in New York, and let's say something price only, you can take price of ice cream in London. I mean, generally these two things, if you look at it, there is no direct relationship as far as the practicality is concerned, right? So these two things become for them the covariance would be somewhere very close to zero. This is how this number will become almost, because there is no direct relationship between all these two variables. So this is what this covariance, if it is covariance equal to zero, this is what it will be. And if covariance is less than zero, then it will mean that there is an inverse relationship, that if some variable increases, the variable A increases, then the variable B will decrease. That is what it will mean. Okay, so inverse relationship. But then it will only give you to a point of, that how this is like, because this can take any number. Like right now we have this number, right? But then actually it can take any number. It could be 50, it could be 100, it could be anything. It could be 0.02 also. This number for different situation, 002, whatever. It can be any number. This is also positive number, but it will only give you some direction. It doesn't give you any significant, like how it is. I mean, more than the directional idea, we won't get anything from covariance. So there is another parameter. What we can do is, we can divide this by standard deviation of x and standard deviation of y. I mean, these two are x and y series, as in this case, this is price and area of the floor or area of the house. So if you divide it by both the things, then what we get is something called as correlation, the coefficient of correlation. So that will be very, very important parameter, because that number, if you divide it by the standard deviation, this number will become very, very small, essentially very between -1 to 1 only. Mathematically, if you just divide it by standard deviation and this. So now that will give us much more glimpse that what is actually happening. We'll see that. Okay, so now you look at it, the same thing, similar kind of scores that we are talking about, like a SAT scores, this kind of data set. And so there are two things. This 344, initially we were trying to look at it. We just plotted this on scatter plot. But now let's have a look whether there is a relationship between reading and writing. If the person's reading is increasing, his writing score is also increasing. So these two are numbers. And what we have done is, so covariance, the same way we can calculate the covariance. But then if you take the correlation coefficient, wherein you are dividing it by the standard deviation of both these numbers, the multiplication of it becomes 0.94. Now, so this correlation coefficient, this is a very important parameter again now, that this correlation coefficient will always be in the range of -1 to 1. Okay, this correlation coefficient, which means that okay, so this will always be in the range of -1 to 1. And now how we'll interpret this number, because if you had to interpret this coefficient 21,155 or 3 crore 71 lakh or whatever number, that becomes very difficult. But this number is easily interpretable if the value is close to 1, or if it is exactly 1. When do you think this will be exactly 1? Like if there is absolute relationship between writing and reading. For an example, let's say we'll take this itself. And put this here. let's say instead of this, if some number I'm just putting randomly. Let's say instead of reading and writing, and I have another variable called x, some general variable. Okay. Now, and this is writing. So let's see these two things. So this is one scatter plot where reading and writing is, being plotted on this scale, both on both the scales. Now what I'll also do is I'll plot on another graph this. So can you see the difference? Here, the reading and writing are basically the plot for reading and writing is available here. And this is also linearly dependent. If one is increasing, other is also increasing. Reading is increasing, writing is increasing, reading is increasing, writing is increasing. So both of them are increasing. In this case also, with the writing, we have plotted x. So you see, this is an absolute relationship. In the same order as the writing number increases, the x number is also increases. So correlation between this will be absolutely 1, right? Can you see this? So the more on the straight line, if it is coming absolutely on the straight line, all the point, then the correlation between these two things is perfect. They are absolutely correlated. But in this case, it will be very close. It will be definitely very close because it is still a linear relationship. Are you getting this point? So we can see this correlation. For an example, we pass this number and we pass this number. So which is 94.93. And in this case, how the correlation will be? This, comma this. You see this, right? This is absolute correlationship, and by the plot also we can see this is absolute line. Similarly, if there was a negative correlationship with this, the idea, I mean, like it will be perfectly negative correlationship, means this will be -1. It is ranging from 1 to -1, as I told you. So if it is directly increasing, it means that there will be positive correlationship, otherwise it will be negative correlationship. So this number becomes much more interpretable, that if this number is close to 1, this means that these two things are very, very closely related. Like in this case, reading and writing is very closely related. In this case, writing and x is very closely related. So this is what it will imply, and becomes much more interpretable. So correlation becomes very important parameter if we are comparing two variables which are numeric. Okay. And so this is about correlation. Any questions till now? So what we have covered is univariate and bivariate functions till now. Any questions you have?
No, Austin, I'm good.
Okay, so now what we'll do is, this is also again some data set for real estate and some of the areas in product. Customer information and product information is given. Product is basically the apartments which have been bought. So we can do some analysis. Now see, when you are doing the analysis, these kind of data set will itself come. This is obviously a real data set, but then this has been created in dummy form because it's not possible to give the direct data sets and everything. So what is available in this data set is, these are the product information and these are the customer information. Okay. So product information is like, these are some of the building IDs they have created, and in which building this is the building number, in which year the sale happened, I mean which month the sale happened, what kind of properties are this, apartment or villa or whatever, right? What is the property number and area and the price, okay? price of the property. So this is one thing, simple. This is one data set. Similarly, this data set is about the person who has essentially bought these kind of lands. So it's the name of the person, your customer ID, whether the person is an individual or company or firm or whatever. What is the age of the person, and like that, some information are there. Age of the person, when it was bought, and like these kind of things. Okay. So this is available in this data set. Now, and obviously, when you are working with the data sets, you will get some data set like these points. This is very small still. This is just a sample kind of thing, wherein we have information of some 5,000 people, some 2,000 people in this, and some smaller data set this is. But what we are trying to learn from this is whatever we have learned. So now, based on some kind of analysis we can do, we can perform a lot of analysis. Like let's say that, first thing, as we are trying to discuss on that day, that we can start with the cleaning the data set itself. We first need to understand whether the data set that is there, if there is any kind of, some kind of problem is there in the data set, whether, age, like let's say that someone's age is 150, one possibility. We don't know if there is anything like that. Let's say that if I put this filter here, age at the time of purchase. So some of the people are 19 age, and for some the information is not available. Few people are 76. So maximum age we can see is 76, minimum age is 90. So this is okay enough. But then if there was some information like let's say 120, then it's very kind of outlierish behavior. Why would someone buy a house at 120? That was feasible, but anyway, in this case it's okay. But some of the data sets are, some of the points are not available for some of the people. So we have to see these kind of things, that if there is any missing value, whether the age is correct, if the prices are in the right range or not, or is there a huge variation in these kind of things. So similar kind of analysis, we can do some kind of simple descriptive analysis. Like one thing is here, as you can see that how let's say that gender, in this case, I had given you few data sets. These are like that. There are many other data sets available. So let's say these are the things in this gender category, F, M, and not available. This is how this looks like, right? So if we do simple frequency distribution of this number, let's say I'll take only this part. Okay. And I put simple pivot table around this. Now, let's say by age or whatever gender we're talking about, gender. Count of customer IDs. So how many people have bought the houses or on whose name it is registered? So we can see 108 is there, female is 70. Now what you can do is, let's say that you just put this data, and you can, as we have seen that what are the things we can do, we can create the bar charts, or you can create, but now you have to, let's say that you are presenting. So if you have seen any kind of business presentation or executive presentation, you would have definitely seen that these kind of information are available. Like this is a demographics, which is buying these kind of houses, or they're buying these kind of products and like that. So for that purpose, what we can do is we can simply create some of the charts and show it, and more. So it's more from the point of presentation, whether that is happening or not. Like, so in this case, we can put a simple pie chart. These information are there, but now we don't have this not available. So we have to see this, what is not available or NA means, whether the data is not there, or is it some kind of other stuff that is missing. Maybe that there was a company which has bought this. So what we have assumed in this case, let's say there is a firm that is done all this. So we are just taking this information that 55% of male population are bought, 36% of female population, and you can obviously create these kind of charts, which can be like visual. You can do all these expressions which are available if you want to do it in Excel. So you can always try all these designs and logos and everything to create these kind of charts. So one simple thing analysis we have done. Let's say that you want to see something from the perspective of which location people are buying most number of houses. So similarly, you can do some kind of location analysis, like various in this data sets, we have some locations available, how many people have bought houses in that. Similarly, relative frequency, we have seen cumulative frequency is basically sum of all these numbers, right? If you look at the cumulative number, you know. So if you add these two things, it will become cumulative of this. So total will be 100%. So you can do the cumulative property, and similarly, you can create these kind of charts. So whenever you are making a presentation, you can actually tell them that what is happening. So in California, maximum number of people are buying the houses, which is 66% of the people are buying houses in California, right? And as you move forward, then depending upon however the situation sets up in Nevada and then Oregon, these are the places where the houses have been bought from this particular client. So this is how it looks like. And now from this, what you understand is this number is very different. Like what might have happened in this case is the data that was collected, right? So most of the data might have been collected from the people who have stayed in California. That is why it looks so outliers. Like this is just, in a way, it is just telling you that most of the things is just in this area, 119. So for the rest of it, this is a very different behavior altogether. So in a way, it is also giving us a glimpse at how do we define the outliers, right? If 66% is coming in one particular area itself, then the rest of it is just like, let's say Kansas, Wyoming, Virginia, Utah, all these things become even more irrelevant compared to California. It is very, very, very less. Like you can see, even if you are taking the total 99%, so these are very less, and we can see the frequency also. So this is quite different. The California people are buying a lot of houses. Maybe one reason could be that this particular, client or this particular real estate company is based out of California area only. That's why so many people are from California region. There could be many more interpretations to it. So this is how we begin to do the analysis, and we begin to prepare the judge. All these things right now, whatever we are doing, either through visualization, either through these kind of mathematical, simple statistical stuffs. Simple thing we are doing, it's very statistical part, very, very descriptive part. Whatever is in the data, like let's say that whatever is in the data, right? Whatever we are seeing that, okay, something is missing here. Then based on some analysis, we are saying, okay, this is entry is made by the firm, right? Earlier, the entry is made by the individuals. How do you get to understand this age is not available or gender is not there in this? Because this is from firm. So you may not get directly from this idea, right? That what is this NA? But if you look at the whole data set, then you realize, okay, this entry was made by the firm. This means that firm cannot put what is the age of the firm. So that is why this is firm. And then you put the analysis, and then you say that, okay, so 9% of the things were done from 9% of the houses were bought from the firms. So, but still, whatever we are doing is from the current data available, we are doing all the analysis. So that is the important thing to understand in descriptive statistics, or whenever we are talking about descriptive analytics, we are just focusing on the data we have had, and we are trying to interpret the data and make them, interpret the data and make them understand to someone. This is the role of data analyst, and more a lot of times of the data visualization also. In data visualization, you may be using some other tools. Like right now, we are using tools in Excel only, where we are creating bar charts, and whatever we are creating. So this is what the largely the part of data visualization and data analysts are. They just understand the data, interpret the data, and show the results in whatever way they want to show. Like it could be in the form of KPIs, as we are saying, or it could be in form of presentations, or these are the things where data analyst role mostly becomes over. But if you are aiming to know more, now what we want to do is, let's say that based on these understandings, that okay, this is the area, this is the price, okay, we want to understand that how this equation, like let's say that how price is dependent upon the area. Is there a, is there a kind of, now let's say that something is there about this price and area, some information is available. So can we find some kind of equation or some kind of relationship, mathematical relationship, that based on that we can predict. Let's say that we have only one variable for now. In this case, there are some other variables. This is apartment time and like that. Okay. So few information is available. Based on that, can we make some kind of predictive information? Can we make some kind of predictive equation? So if you put some equation, let's say that if you put some equations like this, that price is equal to something, let's say 342 plus maybe 2.8 times of area in a square feet. Okay. Plus, let's say for now, we'll just focus on one variable, area in square feet. Now, let's say that by analyzing this, you come to a point where you get, okay, this is the best equation that will represent the price and the area, if the area is only consideration factor. So now if I say that my house is in 1500 square feet area, then it's very easy for me to calculate that what will be the price of this, right? Simply we can do this equation and we can check what is the price of this. So this is still a very simple thing, but what we are doing now is it has not remained in the realms of the data that is available. Now it has become, using the data, we have created an equation or created a situation where we can make some kind of prediction that what should be the price of if the new apartment is coming or something else is coming, they can decide what should be the optimal price in that region based upon area square feet. This is right now only area square feet, but we can have many other variables. So like that, we can create some equation. And when you go to these kind of situations, the role of analysis, data scientists come into picture. So this is what all the modeling thing that I've been talking about is about, finding these kind of equations, that how something is dependent on that, how do we get to that information so that we can make some prediction. Like in this case, price is a predicted price. It may not essentially be the actual price. It's a kind of a predicted price for which we are creating this equation. So that's the objective that we'll finally look at. So now we can, but for descriptive part of it, we can simply have a look at other plots. Like let's say that this is a plot between, age and price. How age, if there is a relationship between age and price, right? So if you look at it, one thing is simple correlation coefficient. Also you can check, which is and obviously we have seen the formula. The formula is available. You can directly put the formula, and in this, let's say that this is your price. Okay, before getting into this equation, age and price comparison, let's have a look at one more thing. Do you see any parameter? These two are different tables altogether, right? This is a customer table and this is a product ID table. Okay. So do you see any parameter which is basically specifying that because how do we get to the first thing is, how do we get to the point where we can compare age and price? We need to have both the information in one table, right? Then only we can compare, isn't it? Hello? Hello?
Yes, Austin. Yeah.
Yeah. So do you think that, how do you think that we can match this customer and product table? Is there a way? Can you think of something? How do we see this contains only customer information. This customer ID is there, and whether the customer is individual or it's a firm or what it is, name is there, and age and everything is there. It doesn't have this price column. Okay. And in this table, ID is there, building, year of sale, apartment, property number, area, price, status. All these things are there. So
Okay.
this is only this only contains information about people who have bought the house. You can see there's a status is only sold. So this is only information about people only thing is sold here, right?
Yes.
So it means that it only has the information. So how do we basically merge these two information so that we can check how is the age and price that person has paid is actually correlated or not? So see, in these cases, what will happen right now, we only have two tables. So in these cases, if you are working with multiple tables, you can have multiple information. For an example, in one of the table, you can have the customer information for a bank, let's say. A customer information is there, all the information about it. In another table, the transaction information of the customer is there. So any two tables to be, now if you want to combine these two tables, there has to be a definite ID by which you can, so it can be customer ID or membership ID or whatever. So based on that, you can actually merge these two things. Okay. In this case, do you think there is any other, any parameter by which we can actually merge these two tables?
The years of the transaction.
So see, whenever we are talking about the ID, membership ID, that has to be very unique to that person, right? There is no other way we can actually merge it. You're getting my point?
Yeah, makes sense. Okay, yeah.
So if you say that if you check at the year of this, then it does not make that you can check multiply this, or you can just check in someone has buy in 2007 and we can merge it. It won't work like that. Whenever we're talking about a membership ID or something like that, it has to be very unique and that has to be available in both the tables. So right now what has happened is in this table, there is no such information. And that's why I was looking at. Because I just got this table. I had not seen this table earlier, but I thought that I'll give you some example for now. But what I'm trying to tell you is that these two tables do not have any such identifier by which these two customers can be merged. These two tables can be merged per se. There's no direct information like this. So it's kind of incomplete table in a way. It's the table, and you'll find these kind of problems a lot of time. I mean, whenever you say to a client that provide us your data, they'll give you some data points, but there'll be maybe no match in the data points. You have to do a lot of research, lot of analysis to understand whether how to combine these two things. So that's why I, in the beginning only told you that data preparation itself takes a lot of time. A lot of time in the modeling process in any analytics project is basically devoted to data preparation itself, because understanding the data, getting data in a situation that can be worked upon itself take a lot of time. And that's the case with many of the analytics projects. Like this, in this case, we are not finding any identifier here, which can basically, get you to a code that you can actually merge both of them. So that's not possible. So we have to figure out some other way. So this data in a way that is not complete. But for now, what we are trying to say is, if there is a relationship between age and price, let's say that we had some information about age and price. So this is what it is giving, that the correlation coefficient is minus 0.7. And if the correlation coefficient is almost very close to this, this means that age and price are not that much related. There's no relation actually. And this scatter plot is also in a way telling you that only. That this is like very scattered. There's no direct correlation. If you plot like this, it's very clear, right? So similarly, if we see, let's say that if we don't have information of this, but another thing that we can do, let's say that I am just trying to plot for these two numbers. If there is a relationship between price and area, okay? So what I'll do is I'll just take these two things out. Put it here. Okay. Okay, so there are no missing values. Some price information is there, and area information if it is available for all the sold flats. Let's see. Okay, area information is also available. There's no missing value in this. All right. And there are 250 or 267 points. Okay, now let's plot these two things on a simple scatter plot or line chart. Okay, now can you see? There's a very direct correlation based on all these points that we have. There's a huge correlation between as the area increases. Sorry, this is not a good way. We can do on the x-axis, we can put the area. Let's go with this. Okay, so let's see this. As the area increases, this is in a square feet and this is in what dollars. So if the area is increasing, obviously we can see that the price is also increasing. So there is a direct correlation between it. Now another thing that we can do is if we change the graph type. Okay, just we'll put some straight lines. So with these 2 points, with these data set, there can be many lines possible, right? It is not one line that is there. There can be many lines possible, but still, the thing is, there is a direct correlation between price and the size in the price, and this is very much clearly visible from this data also. So this kind of analysis we can do. We can try to understand whether how this correlation is between two variables. So these are all part of understanding the data, the descriptive statistics part of it. So see, I've just put this correlation and there's 95% correlation. So there's almost absolutely direct relationship between these two variables. So like that, we can do a little more research on this data, do some more analysis on this data and see how the things are like, by the age we have seen how the things are happening. By country we can see, by state we can check whether the person has bought some for the home purpose, investment purpose or office purpose. Like that, we can do a lot of analysis on these data points. So this largely covers for our descriptive statistics, right? That descriptive statistics essentially contains how to deal with categorical variables, how to deal with numerical variables, understand those variables. And that's what we have done. Now in the next part of it, what we'll do is, we'll learn more of inferential statistics. So what is inferential statistics is, based on some information can we infer something else. Like I was giving you one example of the sample. So based on the sample information, can we infer something about the population itself? Based on information of 5,000 COVID patients, can we infer something about 1 crore COVID patients? So if you come to these kind of questions, then you come to inferential statistics. And that's what we'll cover next part of it. In this, a very important thing that we're going to touch base on is something called hypothesis testing. And that is what we'll cover. We'll cover everything from the lens of intuition, not much into statistics, as I was trying to tell you. But if you go into, because this is not a statistics program, we are only trying to use everything from analytics point of view, from the understanding point of view, whether we are getting to the understanding. Because if you see, like this is one simple file, everything can be, it's easy to explain. I mean, if you have some mathematics background, because otherwise it will get too complicated to make you understand all the, we'll see probability also, probability. Most of you would have studied in your 10th and into school, wherever in a college or wherever. So these things you have to do, but if it is too much mathematical thing, then sometimes it will not be, because it's not of much use for us to go through all these things. But if you are interested, you can always look at more deeper statistics part of it if you have some background of the statistics. Otherwise, this will look too abstract for you even to understand. So that's why we are just keeping it much more intuitive, much more based on the understanding rather than making it too mathematical. So that is, and that's a similar kind of thing we'll do with the hypothesis testing, inferential statistics, and towards all other parts that we're going to cover. Okay, any questions? Any questions for the previous class or today's class?
Austin, just quick question. Can I find this file in the material? Have you uploaded this file?
The files which I was working with?
No, yeah, the random variables and this chapter 2, which I can I can see it.
This
on
one,
the
the one you're seeing on the screen. Oh, okay. I'll just 1 second. What I'll do is,
yeah. So at least I can go through that.
yeah, it's quite mathematical. See, if you have understanding in mathematics like that, and if you have some background of mathematics, then you can definitely use all these things. So then it will be helpful. Otherwise, for us as a data scientist, too much of a statistics is not good. So it's kind of a confluence of all these things that you need to know programming. You need to have understanding of statistics. That's important. If you don't have, then you'll be lost if you're doing any machine learning thing. So that is how we are basically trying to cover the statistics, just from the intuition point of view, that how it works.
Yes, okay. I do have a mathematical background. I need to just see everything. I need to.
I'll
go
send you
that.
this file.
Yeah. Thank you.
Any other questions?
No, I'm good.
Okay, so I'm just putting in the group chat. You can download it from here. It's basically from the internet, and you can find many other files like this. So it's not just one of them. Anyone else has any other questions? Okay. So then we can leave it for the day. But guys, just one more question, because see, statistics like this in Excel is fine. But have you tried something doing on the Python? Because that is very important. If we are, because right now I'm just giving you the glimpse of all this statistics and everything. But Python is very important. Have you tried the commands in Python? Whatever we have learned in the previous sessions.
Yeah, just doing with Python.
Yeah, so because see, a script I have already said. A script I have already said. I mean, whatever we have done in the classes. But it's important that you get it hands-on. That's very important. Otherwise, what will happen is you'll just have some very, distant idea of what is happening. That won't be of much of use. So it's very important that you do hands, at least whatever is available in the snippet. Because what I have given in the class is mostly just the very important part of it. So at least that much you should definitely do it, so that you know how to work with Python. Because unless you know to work with Python, these things won't be of much use. We are not going to do anything in Excel. Everything will be done in Python only. So it's very important that at least in the next week, if you have not done it, give some 1, 2, 3 hours and cover up all the things that we have done in Python. It's very, very important.
Yeah, sure.
Okay. Because tomorrow we are going to touch base again some part of Python with the visualization that we have seen. We'll do in Python also using some plotting technique, PyPlot library, and we'll cover with the inferential statistics part of it, and largely we'll cover up this descriptive statistics or these part of the very preparatory statistics and preparatory part of the analytics that we'll cover in tomorrow's and the next session, which is the next Saturday. So it is important that at least in the next week you spend some 2-3 hours, take out some time and run the snippets that is available in that whatever we have covered. That is at least that much is essential. You can go beyond it. If you don't read these things, that's fine. Like if you want to read these kind of stuff, that's okay. I mean, that's up to you. But that is the essential thing. If you live on that, then most of the things won't make sense.
Okay, then I should focus on a Python. rather
Yeah,
than-
first do that, and then you can see these are like add-on, information or add-on knowledge that you can have. But first, you should focus on the essential parts.
Okay, yeah, sure.
Okay. Okay, guys, then, and we can just leave it for today then, and we'll meet tomorrow again at the same time.
Thank you for attending the session. I hope you all enjoyed it. Don't forget to like and subscribe to our channel. Also, feel free to ask your questions in the comment section below, and we will reply to them at the earliest.